Hey there, folks. We are in our real last content here for lecture today. And I'm going to do a little bit of a whiteboard walkthrough and talk about parallelizing our ray tracers. So a few topics, some might be reviewed for folks who have done systems or a little bit of graphics work before. But I think there'll be something hopefully interesting as far as we're actually going to look at a research paper today, and I'm going to walk through that as we go through today's materials, just so you can see a little bit of the process. And since we're towards the end of the semester, get a little bit of an insight as to where you should be going, what kinds of things you can be looking at to get more advanced skills when it comes to ray tracing. So I'm going to make myself a little bit smaller here, and let's go ahead and, again, just as a reminder, take a look at the calendar here. We are on module number 13, and summer 2 is coming quickly to a close with your final projects due and your homework fours as well. At the end of this week. Okay, so at the end of the day, you're welcome to use your tokens if you need to, but otherwise getting those materials in as soon as possible will be useful, and then you should have the rest of your summer to relax before we see you in the fall, and hopefully see you in the next graphics class or in the future. Anyways, but before we get to that, let's dive into today's topics. I'm going to go ahead and move us here into module 13 and into the slides, and let's go ahead and jump into it. So let me go ahead and remove myself here. And as always, a little bit of a warm-up today. Because today, we're going to be talking a little bit about Pixar's RenderMan, and it's worth looking at RenderMan because this is sort of the state of the art. So this would be something that you'd need to be familiar with if you're, if you've really been enjoying the contents of this course and would want to work at a Pixar, DreamWorks, Industrial Light and Magic, some of these high-end studios as far as the ray tracing side goes, but as well as, pick your 3D tool of choice here. Go put myself here, whether it is a AMD's ray tracing tools, NVIDIA's, Microsoft, etc. And let me go ahead and open up this link again. But really, RenderMan is just a picking is the point of one of these advanced tools. So this is Pixar's main rendering engine, and it uses now a lot of ray tracing techniques. Previously, it was primarily a sort of software render, so doing everything on the software, sometimes using ray tracing techniques, but we'll get into that to see a little bit of the evolution. But anyway, here's a little bit about RenderMan. You can get sort of an overview of what it is, how it's been used in all of these different films, which is pretty cool. And then just get an idea again of what's going on here. So anyway, here's a few projects. That's pretty cool. Very, very powerful for what it can do. You can even see some of these things that it can do, like we've seen in our ray tracers, or at least a little bit in the second Shirley book, and maybe the third Shirley book if you have ventured in there for your final project, where, since this is in production in movies and they want to sort of test things out, you can do different sampling rates to get different effects in your scene before doing the sort of production ready scene here with everything sort of looking nice, which is kind of cool just to see that again used in production. So again, hair, these kind of effects, all these sort of things are really important. Somebody was also asking me recently about, what they can do to sort of stand out, and I told them, taking on more graphics projects on the side and specializing in an area, if you want to be a graphics engineer, such as, focusing on, well, Pixar is very big on rendering hair and fur and, these different things that you could try to implement would really make you sort of competitive in these fields. Or maybe something with physics or lighting or particles or whatever, that could be a side project, right? And it's very focused. It can just be a little tech demo, but just showing that you've gone a little bit above and beyond is always good to do. So anyway, that's a little bit about RenderMan. You can read a little bit about it, and it is 30 plus years old, which is pretty cool, because we can actually study its evolution as well as use it as a case study as why you should comment your code and try to write software in a nice way. Okay, so anyway, last lecture before we get into today, we learned a little bit about backward ray tracing. That's what we have been doing in Shirley's text. It wasn't, I don't think, ever defined there, but we want to know what we're doing. We've been sort of doing things backwards this whole time, but it's actually an easy technique that works pretty well overall. So that's good. But There are other techniques, right? This is a techniques course, so we need to talk about at least two. Photon mapping would be the other one. So it's going forward in the other direction. And by doing this, you can have multiple passes and sort of get closer to solving, this sort of perfect lighting model, which is sort of the global illumination, where you map everything in your system as a photon, and it's emitted from a light source, and you start from the light first, and then you sort of cast back to the camera in a two-pass system. And this allows you to simulate more things as they are in the real world, because you're more accurately modeling light transport, okay, as sort of photons here, okay? So you get a little bit nicer renderings, or I shouldn't say just a little bit, but a lot nicer in the effects, right? We looked at sort of the shadows under some of these spheres previously, and you can sort of see how they light up or how light converges, this sort of caustics effect here, okay? All right, so as mentioned before on the logistics, A4 has been released and is due very, very soon. You're working on your final projects as well as we wrap things up. And pretty much everyone's grades should have rolled in. Everyone's doing well, as I mentioned. If you're enrolled in this class and following along with the assignments, which everybody has, which has been wonderful, you guys have been doing some great work. It's been cool to see and see in the many different languages. We've had folks use Kotlin, Rust, C++, and Python of our students, which has been awesome. All right, so today's key takeaways, parallel rendering, but also sort of a research paper, I should say, and this is going sort of beyond these texts here. So a few things I want to talk about, and then I'm going to go to the whiteboard and sort of do this as a whiteboard lecture for today. But, we want to think a little bit about the state of the art. Whether it's Incredibles 2. Again, I'm going to pick on Pixar because they're a popular example and likely everyone's familiar with them. But just to talk a little bit about production ray tracer and sort of their evolution, how you can sort of go about or how I go about, I guess, reading papers and working through the contents. And I want to just talk a little bit about the techniques as things are brought up. Okay, so it'll be a little bit of a different lecture than looking at slides. Maybe that'll be more or less exciting. I don't know, but it'll be something different to change the pace up. And anyway, it will introduce you to this graphics.pixar.com, where you will click this link. This is what I want you to do for the in-class activity. And be able to see their actual publications. They're actually pretty fun to read because they're very colorful. That's one thing I love about computer graphics. The technical papers are really cool. Of course, you can always see, view jobs here for those of you looking for co-ops and stuff. But viewing all the publications, so you can usually see what the sort of state-of-the-art thing is per movie that they contribute. So here is, Soul here. Looks like they wrote a little paper here and sent it to SIGGRAPH. This is short. This is a 2-pager, right? So you can read about, okay, what was this scene? How did they create it? So not all the papers are long. They do some other cool stuff here. Mostly folks from Pixar, but you can get sort of the idea here. We're going to read one from Cars because I thought it was a nice one because that's where they really introduced ray tracing. So anyway, that's going to be the idea here of what can be done. They've got some other cool stuff here. OpenSubdiv, which is their other sort of library that they use for modeling stuff, which is pretty cool to take a look at. USD is sort of how they store their information, their scene description. If you ever want to know how data is stored, I think there is from Moana or one of the movies that you can actually download the whole scene and just see how much data there is. And there's various plugins. And then Open Timeline. I'm actually less familiar with this tool. Let's see. Looks like it's just in beta, but it's another little media format, I suppose, here. So some cool things there, and we'll explore in a moment. So anyway, we're going to look at ray tracing for the movie Cars. Okay, and I just want to sort of dive into this paper. Here's a link to it. It's also linked on the resources for today, to talk about how ray tracing was utilized and sort of some of the pragmatic problems associated. And as terms are introduced, I'll go ahead and try to highlight them. Okay, and while I do this, I will also talk a little bit about parallelization on the drawing board. So with that said, let me go ahead and bring in Cars. All right, so here we are. Here is Cars. Here's the paper. And I'm gonna scroll into this just a little bit to make it a little bit bigger, but here you get the idea of what it is. And basically, Cars, and it'll be worth reading through this a little bit, but the big idea was this is how they extended their RenderMan renderer to have ray tracing abilities. Okay, so previously, before reading this, or excuse me, before this movie, they just did not have the capabilities to do some of the cool stuff as easily, or I should say as accurately. Okay, they were using a software engine here. Okay, so you can read sort of the abstract here, but basically this is around the Cars movie, which I think was in the 2000s through sort of 2010s, I think, through Cars 3, but they really introduced this idea. So previously, again, they were using this Pixar RenderMan tool. As always, they have been for the last 30 years, but it had different algorithms for drawing these scenes. Okay, so how I'm going to read this paper, how I pretty much read any paper, is I start with the introduction, and it should be sort of a soft introduction, kind of any reader would sort of understand what's going on here. Okay, so a few things I am going to cite and jump to. I do want to actually take a look at whatever this Reyes scanline rendering algorithm is, and that's the citation here that we'll find for it. But the basic problem they had with this movie is they had really, really big landscapes. You can see how big in the background there are mountainous ranges. The racing courses were very large. So they had a lot of work to do. They had lots of cars to render, and they said they had as much as 75,000 cars as spectators in the stadium to render as well. So computationally, this is very, very complex. So a lot to do. And one of the key reasons to use ray tracing, which we're going to talk about in a bit, but I'm going to highlight here, is to get the correct reflection, shadows, and something called ambient occlusion, which we haven't talked about directly here. But these three things which ray tracing can do well, right? We've seen how reflection works, we've seen how shadows work, and we'll talk about ambient occlusion as well. And ray tracing seemed to be the right tool for them, okay? So before we get into that, let's go ahead and look at what this Reyes algorithm is, okay? So I'm going to scroll down here when I'm reading a paper and I don't know what something is. I do like to look at the actual algorithms here, and here's the actual citation. It's in the book here, the Reyes image rendering architecture. So let's just go ahead and do a little search for that, and we can find it here. And we can find the actual algorithm in the paper here. Okay, so this is something you'd have to do. We see Ed Catmull. This is a pretty old paper, right? 87 here. But I'm going to just scroll down here a little bit and just kind of get an overview. Again, if I'm reading a paper, I haven't looked at this. I've intentionally not looked at this. This is a first, this is a reaction video, I suppose. But in the sense that I want you to see how I'm just trying to figure things out. And usually when I'm reading a paper, I'm just looking at the figures here. And there's some interesting ideas here that I'm just going to take a note of. Okay, so they have a sphere here, which we'd think of, you know, sort of triangle mesh, but they can actually render things into patches, which is kind of cool. Okay, so basically they're just doing some sort of extra sampling or subdivision to get some more detail here. That's what it looks like to me. And I'm scrolling around. We've learned a little bit about this sort of jitter by randomizing where we sample from to get sort of, you know, we use that technique for anti-aliasing, right, to sort of get things do a nice sampling, right? That's what it's talking about here, doing a stochastic, so sort of a random sampling here. And I'm just going to kind of keep scrolling through this, and you can see what things looked like in 1986. Still looking pretty nice. This is the Luxor lamp. And scroll down, and then you can sort of follow the paper trail even further back into the, what looks like the 70s here, as far back as the 70s. So very early origins of computer graphics. Okay, so here's the paper. You know, sometimes you don't have to read them all the way. This one's actually pretty nice in that it provides a entire glossary of these terms here, which is pretty cool. So this is actually a really nice paper that's being cited here. But I just want to go to the abstract here, and I'm going to zoom in on the video here, just so we can see what it is. So this is basically their main architecture for rendering complex images. Okay. So they reduce things, so they have a bunch of triangle meshes, and then they're basically subdividing them. Okay. Let me go to the Pixar research page, which I have over here. Again, that's this tool, Open Subdiv. Okay, and that's what I wanted to show here, where you're basically taking models that have been modeled and then subdividing them further, so you can sort of sample from those pixels. Okay. So that's the idea. Okay. So they call these micro polygons here, and then they're just doing the other stuff like texturing them and so on. And they've got something called a Z buffer. This will be familiar with folks, again, who took computer graphics with me in summer one, the sort of interactive computer graphics course, to figure out which sort of objects we're hitting. We're sort of doing this test with our ray tracers as well. But that is the idea. So they basically just built a little render. They've implemented OpenGL sort of from scratch. It is a software rendering algorithm here. Okay. So let me hop back to that so we sort of have an idea here of what's going on here. We'll get into some of these effects here. So that's the old stuff. So they're really relying on this sort of old algorithm. I mean, certainly they have added features and things. But you know, they really want to start using ray tracing. So that's what they're going to talk about here a little bit. Now with ray tracing, and it's kind of interesting here, and I'll put myself on the screen. And this is the actual concern here. And I'll talk about this in a moment. Let me put the paper back up. I don't know why that closed. But the idea here is when I go zoom into this, we're working with a lot of data. So often one of the problems is with these algorithms, and this is going to come up even when you sort of parallelize, you got to figure out how much data can I put somewhere. Meaning when I'm sort of doing ray tracing, for example, if I'm doing lots and lots of samples, you can imagine that buffer that I'm sort of filling up can get really, really big, especially if I'm doing lots of passes on it. So that's actually one of the big challenges in a production studio that we have to worry about, just in order to make it reasonable to be able to render things in time. So they're going to do something relatively clever here, which I'm going to highlight here, and they're going to have caches for geometry. Okay, that's these cars, and for the textures, so the colors that the cars get, right, that we wrap around them. And that's going to help make the performance sort of reasonable, because you're going to be doing a lot of sort of sampling, right, when we're casting rays out in arbitrary positions and potentially doing it in parallel. That means, you know, we might be grabbing a color from all the way, you know, here, and then, you know, over here on this guy, and then, well, over here on this yellow car here, etc. We're sort of hopping all over the place. So, you know, from a systems perspective, that sort of caching doesn't work very well. So they need to have a sort of clever caching infrastructure here. So okay, so let me continue on with this. I'm go ahead and get rid of my self here. Okay, so that's the idea here. So let's get back into, you know, they're going to use some ray tracing stuff, and they're really going to have this hybrid approach here. Okay, so they're going to say, okay, so we're still going to do this patching strategy, right, from their old algorithm, but when we want to do things like reflections, shadows, ambient occlusion, we need ray tracing. We need the ability to capture that information accurately. Okay, and then they do a nice job citing some of the previous work here. Okay, because you have to know what foundations you're building on. Okay, and again, we're in a sort of non-interactive world, so they have some they sort of disclose that. Okay, so why ray tracing? Why do they have to do this? Well, again, here are the ideas for their shadows, reflections, and ambient occlusion. Okay, so real cars are shiny. They sort of talk about this, and you know, I'm gonna let you read this, so I just want to go ahead and jump down because I've already read this and show you the difference here. And I'll give you a moment to sort of think about this and take a look here, but see if you can notice any differences between the left and the right. And I'll go ahead and get rid of the answers. So if you pause the video and taken a moment to look at this, or maybe you've opened the paper and started reading it because you're interested, which is fine. Well, you can kind of see already on the reflections here, look how the eyes are reflected on this car versus this one. Okay. And that's kind of interesting, right? So you're already getting a better sort of reflection there. You know, some of the other details on the front are pretty close, but you don't get these sort of reflections. Now, why not? Okay. Well, this is where I want to go to the whiteboard a little bit. Because remember, when we're casting rays here, we were able to have a ray come down and, you know, hit the surface here, and then we could cast again, right, our secondary ray. Ray, and then maybe there's some other surface that it hits off of, right, and then it, you know, bounces off wherever. Okay, but if this is the ray we're doing the reflection on, right, we want to be able to capture this color and, you know, have it impact some other surface, okay, depending on what we're doing with that ray. So that's what we're able to do with the right side. Okay, so let me draw a little divider here on the right side, but the left side, you know, we still get a little bit of reflection. So I'm just looking at the front of the car here. You know, it's still sort of, you know, we have this sort of deserty environment in the background with some grass and stuff, a dirt road. It is still reflecting there. So what they actually do here, and I'll just, you know, draw the car here. I don't know, it looks something like this. You get your wheels and the rest of the car going back here, etc. It's a really you know, rough sketch of this guy here. So that's supposed to look like what this does, but anyway, what we actually do is we just sort of cast one ray out, you know, in whatever direction that normal is, and we use a trick. We use something in real-time graphics called an environment map. Okay, environment map. So I just want to define some of these terms in case you've never seen them or if you read the paper. And basically what this is I've taken this figure here, and the environment map might be like a cube or something, or rather you're sort of in a sphere that has a texture with it, and that texture is the world here. So I can just cast out a ray from here into the world that's been textured. It's sort of like a reflection or a crystal ball, I guess. You could imagine sitting inside of a sphere, and it's a mirror. Okay, you're sitting inside of a giant mirror, and it can only reflect once whatever the color is, and that texture is that's attached here is the color that's placed back. So you only get one sort of reflection, one bounce here. So environment map, let's see if we can get even a better idea, or reflection mapping, I guess, is the other technique here. Let's see if we find a good one here. Yeah, so here's the object, and you're sitting inside of a cube or a sphere. It could be either, but you're just reflecting back and retrieving that pixel from the object here. So that's what's going on. Sometimes they call this cube mapping or sphere mapping. You know, you usually do this with a skybox, and you just get sort of one level of reflection there. Okay, so that's what's going on there. Okay, so that's sort of solving the reflection problem. If I go to the paper, for cars by adding in ray tracing. So that's pretty cool here. Okay, so let's go ahead and move on down here a little bit. Let's see. Now, the other thing, so that's sort of the reflections here. That's what's talked about a little bit. Now, shadows are also going to be important as well, right? How do we compute the shadow? Let's see. This is sort of the comparison here for ray trace shadows. So you can kind of see these shadows here. They're coming from both sides. You know, maybe we're casting these from the actual lights or whatever. We have some sources, but these look pretty good. They're pretty soft, right? One side's darker than the other. These shadows look pretty good. So again, here's where ray tracing sort of wins over the interactive stuff. Okay, so in the interactive world, and let's go back to our drawing here. I mean this picture is going to look relatively the same, except instead of our reflection rays, we're going to instead have some car here. Okay, let's go ahead and just draw a car. Here's a car. And it's zooming in some direction. And we have basically the shadow rays, right, that we cast from some our eye, if we're doing sort of the backward ray tracing. And then we have sort of the light source here, and then we see, right, we bounce it towards that light source, and we see if it essentially hits it, right, without intersecting some of the object, to figure out if we have a shadow. Okay, so that was the idea with our shadows. With the interactive stuff, right, so we still have this sort of nice technique, and we can sort of do multiple bounces and sort of we have that advantage. So let me give it a little check mark here. We can do multiple bounces, but the real big thing is, since we're sort of computing this, no storage. No, I shouldn't put no, I should put less storage for shadows, right? Because I'm just sort of accumulating in some buffer, right, what the final image is going to be. What we do in interactive graphics, so here is this guy here, this car, again, it's zooming in some direction, is we actually accumulate in a separate texture for this object a shadow map. Okay, shadow map per object. Okay, and what this means is we're doing this light computation, right? But we're sort of going to then texture on top of this object the actual shadow, or the ground or the race car or whatever, So here's the shadow that we draw on, and that'll show up somewhere on a separate texture map, this pattern here. And this is where things kind of get interesting, because if I have 75,000 cars in the stadium, right, if I sort of look at these, even if they're dots and I'm still trying to compute accurate shadows, I'm just going to put times 75,000. And let's say those are, 4 megabytes, per texture. They might be smaller, they might be bigger, but let's say that's what it averages out to. This here is a lot of memory that we're computing per frame. Okay, and then our cache has problems and all these sort of things. So it's yet another advantage of why they implemented ray tracing to use for shadows. It saves space and you get better accuracy. Okay, so that's sort of use number 2 described in the paper. Okay, so again, a win here. So they're still taking advantage of their rendering. They're using that sort of micro polygons and these patches to actually render the objects. But when it comes time to compute the actual shadows for the image, they're able to sort of composite on top of it based off of the ray tracing computation. Okay, and the third thing that they talk about is ambient occlusion. And they give a nice definition here, saying it's a measure of how much light reaches a point from a uniformly lit hemisphere. Okay. So what this does is, I like to think of ambient occlusion as sort of self shadows, or these sort of softer features here. Here's a nice example of it. They've taken all the textures away and just again, let me leave the definition up here. Figure out how much light reaches a point from a uniformly lit hemisphere. So if you can imagine, like, the sun here is placed or something, how much light can reach each of these points. If it's totally or under the car, you can see it's just not possible for light to leave there. You get sort of this shadow here, not the same shadow rays that we had before, but this sort of just ambient is how much light is in general in the scene. It's one of the components of light. You can sort of think about this as a dimmer switch, if you want, where you can turn it up or down, but how much light can actually reach. So even under this car here, if the world is very, very bright and it's a very bright sunny day, at most you're still going to have some grayness under it, right? Some shadow here, because light just can't reach it. It's being occluded by this car, the body of the car here, if your light source is up here. So that's the idea. And you can do this computation here. Let me go ahead and move over here. Again, by doing just a ray tracing. So you sort of have this, again, uniformly, they said hemisphere, that's what the ambient occlusion is. I'm just going to draw another light source here, and you figure out, hey, if light scatters in every direction, you know, this area can light up, this area lights up nicely, but you're going to get a little bit of a shadow under this car, right? The light rays are just going to intersect, you know, along here on the top of the car before they can reach under this point here. Okay, so again, that's the idea of ambient occlusion. Let me do one more look, because there's a nice, some nice diagrams of this. So you can just see the sort of with and without here. Let's make that a little bit bigger. So without ambient occlusion, you're saying, hey, light, no matter where it is, it can just reach anywhere. With ambient occlusion, you're saying, okay, we're actually going to take into account if rays can't just pass through these objects blindly, so we should darken, you know, these gaps here. That light would be occluded. It would never get to, you know, light up this middle sphere here. It would be occluded. So it's a nice way to make the world look better. So you can read the wiki article on this. Let's see, there's usually a lion's head that people like to use. So, well, that previous example does a nice enough job on it. Okay. So that's the gist of this sort of Pixar paper, and it sort of does a nice job of talking about the uses of ray tracing in this context. Okay, because if you have lots of light sources, you know, computing these shadow maps takes a long time, and you have to store all of them. And really, we just want one sort of final image, right, in one pass. Pixar in reality probably uses a few passes, but you know, we've been using a sort of one pass algorithm for our backwards ray tracers. You know, so this is the texture issue. We get the better shadows. We get the better ambient occlusion, which is more difficult to do in real time. People do real-time occlusion. Let's see. There's actually an example of this, yeah, in Crytek, and there's another, Morgan McGuire has a algorithm on this as well for real-time, but typically you don't see it as, you see it now today, but you didn't used to, I should say. Okay. Now, again, there are a few other things to discuss. We're not totally done with this paper, but we've got the gist of it. But it leads nicely into, you know, how do we ray trace things? You know, big scenes. Okay, so cool that we can do all these things, you know, ambient occlusion. We can have, you know, our rays doing shadows, our rays doing reflections, and so on. But as many of you know, it's probably taking a lot of time to ray trace some of your scenes. Maybe you're even frustrated. So ray tracing can be parallelized, okay? And relatively easily parallelized, okay? Now it's going to talk about this, you know, we have to fit everything in memory sort of idea here. Pixar has a lot of memory. They have very big machines with lots of RAM and many machines working together, so they can solve this problem. But we can too for the scenes that we are rendering as well. So that's a nice lead into our next topic. You can read about these things, but they basically talk about the cache, which basically keeps stuff that's readily available nearby. So you can speed up things. They then talk about spatial acceleration data structures, which we talked about a little bit. Basically your bounding volume hierarchies, okay, or octrees. And let's see, what else is in here? Motion blur, which we talked about, and we'll talk about SIMD as part of the parallel programming stuff, okay? So for that, I want to dive into the drawing board here. Let me go ahead and give you a little break if you need before we jump into parallelization. All right, and if you've given yourself a little bit of a break and are ready to talk about parallelization, I'm going to talk about what it means to run something in parallel here. So I have a little bit of a drawing here. Some of you might have taken systems, so I can keep this short in a way, but also still be complete to talk about parallelizing our ray tracers. So Shirley talks about this a little bit in the third book. And he even gives a little bit of a warning. He says, just because something can be easily paralyzed doesn't mean you should. But in this case, I think we should. I think it is possible, right? As you implement more features, things can certainly get more complicated. But let's go ahead and talk a little bit about paralyzing your ray tracers. Now, there's a couple things to note here, I guess. Our tool is typically, and let me do this, here I'll do it in black, is a thread. Okay, and this is a lightweight process. It's basically a way that on my CPU, so let's just assume we have one CPU, you might have four, but you can have multiple threads here, which I'm just going to label with T. And these threads can have their own logical flow. Okay, so in a program here, if I have main and I want to do something, in a loop here, let's just say for I from 1 to 100, I'm just going to write this in sort of pseudocode, do something. So this portion here could actually be parallelized, right? As long as the data or the resource that I'm accessing isn't shared. And in our case, well, things aren't really shared because I have, this is my buffer here where I'm drawing to. You can call this whatever you want, your color buffer, so C buffer. Each of these individual pixels, well, they're not going to be interfered with from other rays, right? I'm going to cast out rays from my eye, right? Multiple per pixel, eventually, right? From my source. Here's my eye. And they're not shared. So I can work on independently each of these pixels. Now, of course, you might say, well, what if something reflects here onto another, pixel here that we haven't touched? Well, we might have to sort of pause for a moment. So we sort of do need some synchronization here. So one thing to keep in mind with threads is we like data parallelism. Let me sort of define this term, what I mean by this. We can operate on individual pieces of memory without worry that memory is shared. Okay, so this makes sense from the perspective that we can just, from my eye, if I've only got one, place where I'm casting rays from individually on each of these pixels, right? I'm casting my rays, right? I'm casting my rays and performing that intersection test. So for each of these threads here, 1, 2, 3, 4, 5, 6, 7, 8. Let's say I have 8 of them on my CPU. I can do 8 at a time. So I do 1, 2, 3, 4, 5, 6, 7, 8, and then I move on to the next 8. 1, 2, 3, 4, 5, etc. You get the idea. Where I do the intersection test for each of the next, pixels at a time. So all of a sudden, I am potentially doing 8x speed up if I have 8 threads. Okay, so then I'm just updating this color buffer where I'm drawing everything, doing the intersection about 8 times faster if I have 8 threads. If I have more CPUs with more threads, I can continue to improve the performance. Now, there does have to be some sort of synchronization, which I mentioned. So you might have to do a little bit of organization, meaning you sort of break things into passes, meaning the first pass is you do all of your intersections, right? To see which object intersected at this level. And then you might have to do another pass where you again cast all the rays and then do your sort of reflect rays. Okay, so you might need to do a little bit more bookkeeping and say, okay, for each of these pixels, if I did intersect, reflect, and what you do is you take one of these threads here, another one of these threads, and you sort of queue it up and say, in a queue data structure, next pass queue, and sort of add this guy into the queue here and say, okay, this thing reflected, so where does it reflect to? Okay, maybe it's this pixel here. And do an intersection test and sort of continue out that way. So you might have multiple passes, and you might need some other supporting data structure to sort of organize, well, what happens next when you have multiple passes, right? Your secondary arrays basically is what I'm taking care of, right? And you'd want to make sure you finish all of your intersections in the first pass, and then move down to your next pass where you handle reflections and stuff. Because previously when you're doing things sequentially here, one at a time, you didn't have to worry about ordering. So that's one complication that comes when you start parallelizing things with threads here, okay? And just to be specific, I'm talking about CPU threads since we're doing everything on the CPU. Now you could do everything with on the GPU, right? If you go on to implement your ray tracer on the GPU, and GPUs are massively parallel. They have lots and lots of threads, thousands of threads versus a CPU. In reality, this is probably a quad core machine. I should just draw this a little bit more accurately. So here's CPU 0, 1, CPU 2, CPU 3, and they're all sort of working together. Okay. While I was designing today's lecture, there was a little bit of an interesting case study I saw here. And this looks like somebody's final project here from a few years ago. I was Googling around to find some data. And my question is, we can go back to the Shirley quote. Let me bring myself back up here. Oops, I lose my page here. Let me bring it back. Is your ray tracer always going to be faster if you implement threads? And I'll give you a moment to think about that. And if you took a moment to pause and think about that, depending on if you have, a little bit of systems experience, the answer is, well, probably. It should be faster, right? If I have 8 threads, it should be 8 times as fast. But there could be some complications. So I just want to show you some actual data that I guess this person collected here. I'm going to scroll down to their data, and they talk a little bit about how they did this basically per pixel. They use something called OpenMP here to parallelize their for loop. Exactly what I was showing there, where you have something that you want to do a whole bunch of times on different pieces of data, so different portion of that array where you're doing your sort of intersection test, you can parallelize that, right? So let's go ahead and do the performance. So as you can see, the blue here in the serial, so no parallelism, is higher. That means it's worse in time performance. The ideal here is sort of your optimal performance, but we don't quite get that. And that's because in our parallel program, we have a little bit of overhead to manage these threads, right? So in my drawing here, I drew a little queue, for example, that you might have to do to manage the threads, as well as the operating system needs a little bit of time to actually process, launch these threads. There could be some, I'll just throw the term out, false sharing. So some cache misses that are associated when you have a bunch of threads accessing different parts of data. But overall, if I look at this, right, and let's take one of these samples here. They have some different shapes that they're doing. Let's look at this one's the most easy to see where it lines up with, but roughly, this thing was taking about 4 seconds when it was parallelized first. Let's call this 14, so it's about 3.5 times faster by just using threads and sort of parallelizing that loop. You can do it in about 1 or 2 lines using OpenMP, which is a library in C++ for this. Or if you've done some systems programming and are familiar with pthreads, just launching all of your pthreads and then joining the threads at the bottom here. And 3.5 times faster, which is pretty cool. I don't know if they actually made any other structural changes. I was recommending to have sort of 2 passes and sort of handle, putting all of your other threads to handle reflections and these sort of things. In another queue, you may or may not need to do that, but something to play around with a little bit here, but not too bad, right? It's a pretty parallelizable program here. Okay, so that's one type of parallelism that I want to talk about in your ray tracers. The other that they mention in the paper, and I'm going to draw a little box here because it's sort of a separate category, is true CPU parallelism. And that's with something called SIMD instructions. So single instruction, let me just write it out here, SIMD. Single instruction, multiple data. And basically what this is it says, okay, if I've got a bunch of these pieces of data here, and I'm doing some computation, but I'm going to do it to all of them. So for example, gamma correction, right, where we found a cheap way of just saying, hey, take all these pixels and multiply them by 2. Well, or whatever we did for the gamma correction, not necessarily multiplying by 2, but just sort of surely sort of use that as a cheap technique to sort of, again, differentiate between the colors. But I'm going to apply that same operation to all of these pixels here. So why wouldn't I be able to do that in parallel? Because it's the single instruction that I'm doing is a multiply on multiple pieces of data. So we have special SIMD instructions that can do that on blocks of data, and our modern CPU processors can do that quite efficiently. So I'm going to just open up another tab here, SIMD. Oops. And give you a picture of this. And again, for some of you who had me in systems, you saw this. For some of you, this might be new, so I just at least want to expose this to you. Let's go ahead and the right article to look at is here, crunching numbers. The instructions are called AVX, AVX2, AVX512. This is a little bit of an older article, but it has nice illustrations later on here, or at least a practical instruction of what's going on here. Actually, this is a nice guide, but there are not nice pictures. So SIMD, I'll go back to Google Images for this, just to show you here what's going on. Basically what you get with SIMD is instructions that can be applied. So this is a 256-bit SIMD or an AVX2. And there's AVX512, which means on 512 bits of information, you can execute the same instruction. Okay, now what the heck does that mean? This will be the last topic because it's a little bit of a tangent, but I just want to still talk about some of the parallelism because I think it's cool, because I think you can apply it cheaply on some things like the gamma correction when you do that in your ray tracer. So if I have 512 bits where I can do everything in a snap, and each integer is 32 bits of 4-byte integer. That means 16 integers at a time, or 16, if it's, if we're talking pixels here, where we have a red, green, blue, and alpha component, that means I can, so divide that by 4, I can do operations on 4 pixels at once, okay, versus just 1, if I'm doing the same operation, okay? So if there's a takeaway from this, I just want you to know that you have built-in CPU parallelism on your processors, and they're called SIMD instructions, single instruction, multiple data. And you can roughly do things 4 times as fast without too much effort. Okay, so the actual article to take a look at here, that crunching the SIMD numbers here, we'll give you a little bit of an introduction here, so you can take a little bit of a look at that here. Okay, so that's what I want to talk about with parallelism, using threads, thinking a little bit about the structure of your ray tracers, and that it is a very parallelizable program. Maybe not all of the components right away, because you might have to think a little bit carefully on which pixels are getting modified. But again, if you're doing something like the intersection test, that whole test can be parallelized. You can have different threads, working on that piece of data. So that's what I want to talk about for now. Shirley goes into it a little bit in the third book on parallelizing. Let's go ahead and bring that up here. I believe parallel. Let's see. Oops, I guess I did a little search here, and he doesn't really talk about it too much here, which is a little bit surprising. So, it would take a little bit of thinking. The reason he doesn't go into it is because it's not as trivial. Again, it's just one thread per pixel, because I said you might have rays that sort of bounce multiple times, and you might want to account for that to figure out what the final pixel value is as far as the color for that pixel. But you can sort of queue up those computations by just pushing everything into a queue, a first in, first out queue, FIFO, and that's usually what folks do. So a little bit of an introduction here. It's sort of a next step thing that you can do with your ray tracers that I think will be cool. Parallelizing them will certainly be something that's cool. So we got a little bit of exposure to parallelization, and a nice example from the Pixar folks. Let me bring that back up here on where ray tracing is used, how it's used a little bit as a hybrid, meaning that they're still doing their work with polygons as far as drawing and sort of doing the software render, but they're using rays to actually do some of the computation for shadows, reflections, and these things, and sort of compositing that into a final scene here. So I think this is pretty cool. I think this will be a great resource for you to look at some of the research at Pixar as you go a little bit further, and just take a look at some of these publications, and that's one way to sort of, again, gain experience. Again, somebody was asking me about this, but these papers usually aren't super long. Usually a few pages, maybe 8 pages. This is a little bit longer one. And you don't have to read it all and understand it all at once, right? This one, look at this and already say, oh, a lot of scary math, but start with the introductions, start with the abstracts. Then you can even just kind of jump and look at the figures and try to understand what's important, right? What's the little caption at the bottom telling you? And then you can look at this picture and then go back and read the paper. And then finally go and try to understand the math when you need to implement this, right? And you'll find patterns as you sort of do this over time. Again, if this is something that's going to be of interest, or if you're trying to do sort of a deeper dive in your final project or beyond. Anyway, so I'm going to leave you there on some advanced stuff, and then we'll wrap up the course in the next lecture. I'm looking forward to seeing your projects. I've seen great stuff so far, and I'll try to share those with your classmates as well. If you have questions, please let me know, and we'll see you soon for the last time for this semester, but hopefully a little bit after there.